Welcome to the PMDK part of our summit, the PMDK track. We're going to kick it off with a half-hour discussion of the state of PMDK. I'm Andy Rudoff. I'm the lead software architect at Intel for persistent memory. And joining me is Piotr, who's our chief architect for the Persistent Memory Development Kit. So if we go on to slide 2, I'll tell you what we're going to talk about in this half hour. I'm going to kick it off with a brief historical overview, pretty much how we got to where we are today. I'm going to pass it over to Piotr, who's going to talk about the directions and the goals of PMDK. He's going to talk about the current state of the project and give us a look on where we're going in the future. So if we go on to slide 4, going back to about, 2012 or so, we knew persistent memory was coming. We got a bunch of companies together, talk about what should be the common persistent memory programming model. If you've ever heard us talk about the programming model or looked at any of our slides, you've seen this diagram on the right. We had to tackle problems like how do you name persistent memory, how do you enforce permissions, how do you manage it? And well, the short answer is it's done as if persistent memory is just a big file. So you access it like a file, you use the standard file APIs. When you memory map a file, that's what gives you the direct access to persistent memory. This came to be a very well understood and clean programming model that was published by the SNIA NVM Programming Technical Work Group. And if we go into the next slide, I'll kind of show you the timeline there. We formed the discussion, the technical work group, in around June of 2012. We had a tremendous amount of interest, immediate participation from all the operating system vendors and a lot of software vendors and hardware vendors. By January of 2013, we were ready to have our first summit. We actually called it the NVM Summit at the time. We've had them every year since then. By July, we created our first thought experiments on how you program with this. And it's still there as kind of a historical example. There's a repo called Linux Examples. You're free to look at it. But really, PMDK replaced that as a much more mature set of libraries for programming. In January of 2014, the Twig published the first revision of the NVM programming model. So you can see this model's actually been around for a number of years now. We've been building on top of it. We'll kind of talk about how we built on top of it. You know, if you just open up a file of persistent memory and map it and give it to a programmer, it's like saying, here's a pointer to 3 terabytes of persistent memory. Go to it. That gives you everything you need, but it's not really very friendly. We wanted to make persistent memory programming a lot easier, and that's really the primary goal of the PMDK. We went around gathering priorities, and I've listed the top 4 priorities here. People needed a way to track persistent memory allocations in sort of the malloc and free programming style, but persistent memory aware. Needed a way to make transactional updates so that if your program crashed or if your machine crashed or had a power loss or something like that, your data structures were still in a consistent state. And that's some tricky programming, so you really don't want to have to reinvent that every time. People also wanted, the common containers like lists and queues and hash tables and so on. And they wanted tools to make persistent memory programming not so error-prone. So we took these goals and we use them to guide our development of the persistent memory development kit. So that's kind of the basic introduction. I'm gonna hand it over to Piotr now, who's going to dive into the details. Go ahead.
Sure. Thanks, Andy. So I'm Piotr, one of the developers behind PMDK. I'm going to be walking you through the rest of this session. The key direction of PMDK that underlies everything that we do is solving real-world problems using PMem. Persistent memory is a multi-dimensional technology that can be applied in a multitude of ways, depending on the exact problems being tackled. As memory, it's both more affordable and bigger than DRAM. This enables memory-bound applications to vertically scale beyond what would be feasible with traditional approaches. As storage, it's significantly lower latency than existing solutions, allowing for very fast operations that require strict durability guarantees. It also doesn't require page cache, as traditional storage does. But to fully benefit from PMem, it has to be considered as both memory and storage, enabling new unique solutions. I will briefly go over each of those dimensions and then explain how PMDK helps application developers solve real problems using PMem. As I mentioned before, PMem is larger but slower than DRAM. This makes systems deploying it heterogeneous. This presents a challenge because typically applications assume that all memory is the same and might not operate ideally when that assumption is violated. There are ways to transparently allow applications to leverage PMem, like caching or tiering, and those work well when the hot working set fits into DRAM available on the platform, leaving PMem for colder data. But if the application doesn't work well with such transparent solutions, applications might want to explicitly manage data placement, allowing for better memory locality control. In those situations, PMDK has tools to help applications manually manage memory allocation policies. Like we just talked about, when compared to DRAM, PMem is bigger but slower, whereas with storage, the situation is reversed. It's smaller, but still quite big, up to terabytes in size, but much faster than a storage array called B. PMem is a similar disruption to storage technology as SSDs. Solutions developed to handle HDD SSD heterogeneity of the storage stack work just as well with persistent memory. However, one important characteristic of PMem when used as storage is that it can be used without a page cache that will typically be required for traditional storage. This allows solutions that heavily rely on the OS page cache to potentially improve tail latency as well as reduce DRAM usage. While PMem can be used transparently as storage in most applications, PMDK can help some existing applications to improve performance even further. Lastly, let's talk about PMem as both storage and memory. This is the most interesting bit, at least for me. Existing data solutions, like databases, for example, are internally designed to combine memory and storage in one cohesive system. PMem is a technology that theoretically allows such solutions to simplify their internal design such that everything is stored on PMem. And while that is certainly possible, and does lead to a simpler design, it does have its downsides, like lower performance than a pure DRAM in-memory system, or lower capacity than a typical database that spills over to disk. Persistent memory should be treated as a new tier in between memory and storage, and integrated into solutions with a holistic view of the architecture. There are many techniques enabled by PMem to improve latency and overall efficiency of a system. For example, solutions that require failure atomicity can now be durably write logs with cache line granularity instead of a block one. PMDK implements many algorithms and data structures that enable developers to create systems that efficiently utilize PMem. Given all of the functionality and diversity of solutions that PMDK helps with, it's also our goal not to overcomplicate stuff. I really like this quote from Larry Waltz, who said in his book about Perl that Perl is designed to make easy things easy and hard things possible. This is definitely a worthy ideal, and with PMDK we strive towards the same thing with our design and architecture of our multi-layered solution stack. And speaking of which, let's now briefly go over what's available in PMDK today. PMDK is a suite of libraries and tools for PMem. The libraries can be broadly categorized into three categories. Libraries for volatile use cases that allow applications to easily utilize the capacity of PMem without necessarily having to worry about failure atomicity. Libraries for persistent use cases, which allow developers to create fully failure atomic and safe solutions. And finally, libraries for remote use cases that can be used to augment either volatile or persistent use cases with remote memory access capabilities. For a volatile use case, we have two libraries, libvmcache and libmemkind. Libvmcache is an in-memory embeddable caching solution, whereas libmemkind is a memory allocator that enables allocation of different types of memory, like DRAM or PMem. The latest release of memkind also exposes an API for heterogeneous systems, where memory is allocated not by its name, like DRAM or PMem, but by its property, like latency or capacity. For persistent use cases, PMDK has a comprehensive stack of solutions where one builds on top of the other one. At the very bottom, there is libpm2, a new major release of libpmem with significantly improved functionality. This layer provides just the bare essentials an application might find useful when creating and using PMem. Next, we have libpmj and its C++ bindings. Those provide general purpose allocation and transactional facilities, and also specialized data structures for PMem. And on top of all that, we've created PMKV, which is a very easy to use key value store for PMem. This is also where we try to support a wide variety of higher level programming languages. Tying this all together is librpma, our library for simplifying the use of PMem over RDMA, or remote direct memory access. It can be used in conjunction with any of the libraries that I've talked about. In addition to the libraries, the persistent memory software ecosystem also has many different tools helpful in creation and then deployment of PMem-enabled applications. Some of those tools were made to aid in the development process of PMDK, such as PMjack or PMreorder, but all of them are generic and can be used in any context. That was the present. Let's now look at our plans for the future of PMDK. The things that exist today in PMDK focus primarily on exposing persistent memory. This seems obvious, given the name of the project. However, PMem, like we talked about, does not replace memory or storage, but rather slots in between them in a larger heterogeneous system. What this means is that developers that use PMDK still need to take into account the existing DRAM or disk resources that an application might want to leverage for better performance or higher capacity. And that's fine. This flexibility was the original intention behind most of the libraries in PMDK. But still, we see an increased need for more comprehensive solutions that would holistically fit into a heterogeneous memory and storage ecosystem. That's why we are now working on more flexible solutions that embrace heterogeneity of modern hardware. The first one of those solutions is a new hybrid engine in PMKV that leverages DRAM for better performance compared to the existing persistent engines. You will be able to learn more about this on a dedicated PMKV session later today. We are also expanding Memkind to include support for heterogeneous memory. The first result of that work is already done. The new version of Memkind enables applications to allocate memory by specifying the desired properties of the memory, like low latency or high bandwidth, instead of specifying its name, like DRAM or PMem. libmemkind will automatically choose the appropriate memory depending on what's available on the platform. This allows for a more generic approach to designing solutions that utilize Memkind. We also want Memkind to be even easier to use. And with that goal in mind, we are working on a library for transparent memory tiering at the malloc level. And finally, we are also working on a research prototype, Onesie, a heterogeneous heap with log-structured asynchronous transactions. The idea is to create a unified interface for data access that can efficiently run on systems with just regular DRAM and SSDs, but also systems packed with modern technology, like NVMe or PMem. This will give developers an easy-to-use interface for their memory and storage needs that will scale with the hardware that it's running on. Onesie is an embeddable solution that is being implemented in Rust using its native async support. It exposes ACID transactions with automatic memory management and transparent tiering across different types of memory storage. We are hoping to publish an early version later this year. And that's all we had for this session. Thank you for joining us today. Enjoy the rest of the summit.